model here, and it's the same as the before. The first model I'm again going to talk about is a random network. But the random network which I'm going to talk now, it is going to be a more standard model as compared to the last time. These voices of construction are sort of disturbing me. I hope they are not audible to you. How are we going to make this random model more standardized? You see, last time what we did in the hands-on, so you have 121 students here, and we sort of fixated that maybe these 121 students, they will have 178 edges between them. Then we'll randomly pick pair of people and add edges between them. But you see, mostly you wouldn't know how many edges or how many friendships would be there between these people. So instead of doing it in that way, fixating on the number of edges, will be doing it in a slightly different way. So take a look at this. Instead of, let's say, 121 people, assume that I have just 5 people. 1, 2, 3, 4, 5. And now there can be a whole lot of friendships between these people. How many? There are possible 5 choose 2 friendships, which is what? 5 into 4 by 2, 10 friendships, right? And we don't know out of 10 how many will happen. So to model it, what I'm going to do is I'm going to toss a coin. I right now have a coin in my hand. For each of the possible edges, I'm going to toss a coin and let's see how this network looks like. And then we'll use the same idea and we'll try to code it. I'm first tossing a coin for, let's say, this edge 1 to 2 here, and let's see whether 1 and 2 will become friends with each other or not. Don't know if you could hear this coin toss or not, but I got a tails here, so 1 and 2 are not friends. Okay, let's do it for 1 and 3. Again got a tails. Oh, I'm again got a tails for 1 and 4. Seems like I lost my coin. 1 to 5. I now got a heads. And let's say from 2 to 3 now. I again got a heads. And then let's say from 2 to 4, I got a tail. 2 to 5, I got a tail. I'm sorry, it's a heads. 2 to 5, it's a heads. And let's say 3 to 4, it's a tail. 3 to 5, it's a tail. 4 to 5, it's again a heads. So this is the network which I got here. And now some of you might be thinking that I have fabricated the results. So maybe you can redo this experiment at your own end. Toss the coins and maybe you can put your network in the comments if possible. I don't know if you can post pictures in YouTube comments. Otherwise, you can send a network on Discord. But this is the network that I received. So for every edge, I tossed a coin, that's all. And then I got a random network. So far, so good. I hope that the idea is clear to you. And let's now try to write a piece of code for this same experiment that we just now did. But you see, instead of 5 nodes, let's take 121 nodes, right? Now it's not possible to toss a coin for all the possible friendships on 121 nodes, right? That will take a day of coin tosses. So let's actually write a Python code for that. Let our computer make our work easier for us. I hope my screen is visible to you. Let me just check. Share screen. Yes. Let me create a new Jupyter notebook, and I'm again creating a standard random model here. Let's import our libraries and classes. Import iGraph, from iGraph, import all other classes. Run this cell with shift enter, and then let me make a graph here. G equals to graph. I want to keep this graph undirected, so I'm going to write directed equals to false. you can quickly look at the summary of this graph. So it says that it's an undirected graph with 0 nodes and 0 edges. So far so good. I want 121 edges here. So let me add 121 vertices, and then you can again ask for the summary of this graph. It tells you now undirected graph, 121 nodes and 0 edges. Now next what I want to do is for each possible edge, I want to toss a coin and then decide whether I want to put it in this graph or not. How do I do that? First of all, I need to generate each possible edge, each possible combination. Let me do it like this. Let me say for I in range 0 to 121, right? Those are my node indices. So if you want to take a look at this, I'll say, tell me v dot index for v in g dot vs will give you the indices of all the nodes. So g dot vs is the vertex sequence. I'm saying take every vertex from that sequence and make a list on its index. Right? So you got all your indices from 0 to 120. Right? So vertices are numbered from 0 to 120. You have 121 vertices. So what I'm going to do next is for I in range 121, for j in range 121, and I think that will give me all possible combinations. I now want to toss a coin. How do I toss a coin in Python? If you know it, post the video, comment it, and then resume it. If you are back, you might have figured out a way to do it. This is going to be my way of doing this. I'm going to import this random package, and I'm actually going to make a list called coin. This is my own way. You can use an easier way. I like doing things in a slightly sophisticated, complicated way. I'm sorry. So I'm making this list called coin, which has two ends, heads and tails. And let me say r equals to random dot. So I want to choose one of these randomly. Is random dot choice coin. Right, let me see if that works, and then let me print r every time. So right now I'm not adding edges. I'm just checking whether this random dot choice is working perfectly or not. And well, it looks like it's running all these times every time it tosses a coin and tells you whether it's a heads or a tail. So far so good. So since it is working well, instead of printing r, let me say if r was head, then you add an edge in my network from I to j. Otherwise, you don't do anything. So I don't need any else. Let me run this code. It takes some time to run. I think took 3 or 4 seconds. And then before plotting the graph, let me check the summary again. So it says I have 121 nodes and I have 7,391 edges. Now something looks wrong here. 7,391 edges. Let me first check how many total possible edges are there on this random graph, on our graph, sorry. So it's 121 into 122 by 2, 121 choose 2. And you see my possible number of edges are only 7,260, but it is making 7,391 edges. That's a bad result, because if you look at the density of this graph, it exceeds 1. And by our definition of density, that should not happen. And now you should help me out with this. So again, pause this video, write in the comments what went wrong, and then come back. So if you are back, what you would have realized is we are actually adding a whole lot of edges, and the problem is the way our for loops are running is incorrect. I goes from 0 to 120, j goes from 0 to 120, but you see j should not really go from 0 to 120. Why? Why is that the case? So you see, if there were, let me explain it with a simpler graph. If I had these vertices 0, 1, 2, 3, 4, 5 nodes that we took, how many times should I be tossing the coin? We should be tossing it for 0, 1, 0, 2, 0, 3, 0, 4. right? And not for 0, 0 first of all. So that's one flaw in this code. I goes from 0 to 121. J also goes from 0 to 121. Now maybe you think about, I can put a condition here and say if I is not equal to J, right? To avoid self loops. But then that alone is not enough. You see, because even if you avoid self loop, in the next iteration, I becomes 1 and then J again runs from 0. So you have already tossed a coin for 0, 1 and then you are again tossing it for 1, 0. That is what is giving you extremely large number of edges. Don't worry if you didn't understand it, you can take it up in Wednesday's class and I'll explain it again. So the point is we are not generating the permutations here, we are generating the combinations, all possible combinations. I'll actually change this code and my J should go from I plus 1 to 121. So when I is 0, J goes from 1 to 4, then I becomes 1, J goes from 2 to 4, I becomes 2, J goes from 3 to 4, so on and so forth. It's some basic maths and programming here. And I'll run this code again and see if it settles or not. Let me get the entire thing together. So I don't want to add edges on the top of my original graph. I'm going to redo all this code again. And I'm again going to generate this graph with no vertices, no edges. Add 121 vertices to it and run this code. You see, if you don't do these two steps and only run this code, it's going to add some additional edges on the top of your previous graph. We don't want that. We want to generate the graph again. And I did that. This time it was pretty fast. Look at the summary. This time I have 3,558 edges out of 7,300 edges. And let's look at the density of this graph. It is close to 0.5. So that's how I've been generating a random graph here. What is still the problem? Look at the density. You see, it is so high. Density is 50% here. Right? The density is 50% because we are doing a coin toss for a friendship. That's what goes wrong. So coin toss, you see, it shows you head with a very high probability. So we are saying there's a 50-50 chance of a friendship happening or not happening. If you take a 50-50 chance, your density is also going to be high. So you should actually put friendships with much less probability. And how do we do that? I actually don't want to toss a coin here. Or let me put it this way, I don't want to toss a fair coin here. You should actually be working with a biased coin, something like that was there in the movie Sholay, but that has heads on both the sides, not that way, but a biased coin, which shows heads with a very low probability and tail almost all the time. How do I do that? How do I simulate a biased coin in Python? Let's say I want a coin which shows you head with probability 0.001 and shows you tail with rest of the probability. So 0.001 chances of a friendship happening. How are you going to do that? Again, if you know the answer, you can post this video, post your answer in the comments. Right? So those of you who write in comments, for you, I'll definitely be sure that you're watching the videos. If you are back, let's see how we can do it. I'll tell you my way of doing it and then we can discuss it in the next class. Instead of making a list now, I'll say I'm going to choose a real number uniformly at random from 0 to 1, and if this number is less than 0.01, I add an edge. What's happening here? So I choose a number randomly from 0 to 1. You see, what is the probability that this number is less than 0.01? Think about it. And that probability is also 0.01. You see, what I'm saying is, pick a number randomly from 0 to 1. What is the probability that this number is less than 0.5? You see, the probability is also 0.5. What is the probability that this number is less than 0.7? Probability is also 0.7. That's what I'm doing here. So that's how you can simulate a biased coin. Let me run this code again. Let's look at the summary and you see number of edges go down drastically. It now reaches 60 edges. And if you look at the density of this graph, it's what? 0.8%, right? Now my question to you, we don't want a density of 0.8%, I want a density of 2%, right? So what should be the value of P here? That's question number one. So I'll repeat my question. If you look at the density of this graph, it's 0.008. I roughly want a density of 0.02, right? The one that we had in our original friendship graph. So what should be the value of P for that? P means this probability. So right now I'm putting every edge with the probability of 0.01. So this kind of a graph here, it is actually called GNP graph, where n is the number of edges, p is the probability with which you are putting every edge. So currently the graph I am creating is on 121 nodes. Probability of placing each edge here is 0.01. So this is my n, this is my p, and with this n and p, I get 60 edges. But I need little bit more edges. If you remember, we had 178 edges in our network, right? 178 edges with 2% of density. So how should I change this p over here to get, let's say, 178 edges and lower density? I'm sorry, a little bit higher density than what I'm getting right now. So I'll leave you with that question and we can discuss it in our next class. And next, I'll ask you one more theoretical question on random networks coming up in the next video, or maybe we can do it right away. Just give me a second. It's again a food for thought, something which we'll be discussing in the next class. Let me share my other screen. Okay. My next question to you, it's again for those of you who like maths, not programming based, slightly maths based. So you are given this random graph, let's say G and P, where n is the number of nodes, P is the probability of each existence of each edge. If you create a network like this, you see every time you run this code, you will get a different network. Right? In a while, I'll visualize that network and show it to you. I should have done it. I'll do that in a while. I'll show you that every time you simulate this with Python, every time you'll get a different network. Every time you will get different number of edges. So let me say I represent number of edges as m. So if you create this graph, simulating it with Python or on a notebook with coin toss, you get m edges in the network. And as Athav said, every time you run this code, you'll see a different network because it's a random network. Every time you'll see a different graph. So can you tell me what is the expected number of edges? You see, I cannot comment on the actual number of edges because that's going to differ in each run. But what is going to be the expected number of edges? So you see, similar to a coin toss experiment, you cannot comment on the exact. So let's say you toss a coin 1,000 times. Can you tell me how many times will you get head? Maybe no, every time you will get different number of heads if you do this experiment again and again. But can you tell me on an average how many heads will you get? So this is a similar question. If you run this simulation again and again, can you give me an expression in terms of n and p that tells me how many expected number of edges are going to be there? Trust me, it's a very easy question. If you have the answer, post it on Discord and I'll consider giving you some brownie points. But your solution should be detailed, not just the answer. I should see some work done in there. So let me just switch back here and show you that every time you'll get different networks. Just for the, you see, just for the sake of clarity. And you can say completion. If I come back to this code, let me also plot this graph. Let me say igraph.plot g and vertex.label. I want to label each vertex with its index. v.index for v in g.ps. And let me take a smaller graph so that you can visualize this easily. let me say on 30 nodes. I'll change it to 30 at all the places. And let me do the plotting here so that we can easily run it again and again. Got an error here. igraph.plot g. I think it's underscore. Yep. You see, this is the graph that you get first time, and you see it is disconnected because maybe my probability of connection here is very, very low. And you see, every time you run this graph, it is disconnected. You don't see a giant component in here. I don't see a giant component if I keep this probability as 0.01. So let me just increase it slightly. And you see now you start seeing a giant component. So that is another question. At what value of P will you start seeing a giant component? But you see every time I run this code, you see a different network. And the question is, can you tell me on an average how many edges will you see in such a kind of a GNP network? We'll discuss it in the next class. In the next video, I'll discuss one more model and an associated question, and then we will stop.